Okay, so in my system, I have all these modules loaded. Uh, Modules are actually driver modules or specific plugin modules that the kernel loads in to handle a particular driver or handle a particular hardware. For example, if SND HDA Intel, this is the one which is responsible for handling the uh, onboard audio on my system. Similarly, there are other SND stands for sound actually. So whatever is prefixed with SND underscore, it means they are all related to the hardware, related to the onboard audio. Similarly, there is KVM AMD, which you might have heard about, is the kernel virtualization module. This allows virtualization to happen, running systems, virtual machines with which execute the instructions directly on this computer rather than creating the whole complete machine in virtually, which actually improves the performance of the virtual machines. Then similarly, there is this driver which is responsible for my wireless network card, and there's UVC which is it handles webcam video. UVC video is the one which is responsible for this one. UVC is much more core of that things, core of that module. So in the lsmod list, there is this command lsmod, which actually shows you the module list, and it basically shows you what's the module name, what's the size of the module, and bytes, and then it is used by I don't really know what the number is actually. Maybe if you know what the number is, please leave a comment here. But and then the other one is the used by, which other some modules have their own dependency tree. For example, this SND sequencer, this is a sequencer module. This module is used by SND sequencer dummy. This module is actually dependent on this module. Similarly, if I search for AMD GPU, which is my graphics driver from AMD GPU, it uses all this additional driver modules like DRM exec, all this video module, DRM display helper, all of this. Then the NVMe driver module, which is responsible for uh, letting me use the NVMe SSD, and this is again NVMe is dependent on NVMe core. I think NVMe stands for how many dependencies it has. This 4 designates how many dependencies it has. Maybe. Yeah, but the thing is, now we know these modules are loaded up and these are running and actually helping me use my complete system. For example, if I don't have the AMD GPU, I cannot take the full advantage or use the full capabilities of my dedicated graphics card. Similarly, 80211, and these are all for 80211, which is the standard for wireless communication. And these modules are actually helping me access my wireless network card. But the question now comes up, like how and when did all these drivers got loaded? So for example, in the last video uh, we saw that when the system loads, it okay, I messed it up a bit. Forget this one. I will show you the RxRJ Linux running on my local now, on my actual machine now. But the thing is, we want to know at which point the drivers got loaded and who is responsible for loading them. So the general idea is the kernel starts up, it then it starts the set sets up the hardware interfaces actually much more prudent to say interfaces, all the interfaces which lets us communicate with the kernel. And of course before it basically sets up the system. This actually system, I'm using the name system, but it has, there are many components to it, much like, initialize the hardware, then initialize the scheduler for, running processes, then initialize interrupts so that, interrupts driven IO can happen, and many more things which the kernel is responsible for, but all boiling down to managing the hardware and managing the processes and creating a bridge for the processes to access the hardware through the kernel. All this, after all this is set up, kernel interface startup, we saw the init process is started. This is the thing we saw it in last video. So the kernel starts up, sets up the system, sets up interfaces, which lets user space programs communicate with the kernel, and then it starts the init process, which is the number of process at number one, PID number one. For example, if we see it here, if I say PID, yes, to PID root, this is the user lib systemd. In my system, this is systemd is running, so this is why systemd is taking the role of the init process, and it is responsible for eventually starting all the services directly or indirectly, because some services, for example, if for example, let's say login. So systemd is the parent of login process, which logs into my user, which then starts the process called start hyperlength. Start hyperlength in turn starts hyperlength, and then in hyperlength I am running this terminal foot, and then there's that wireless WL frame, which is my wallpaper utility, and then anything and everything that you run is actually, although systemd has not started hyperlength directly, but it is responsible for hyperlength indirectly, in the sense this one process actually started login, and then which caused the chain to start. So eventually, initially, this is the first process that in the PID1 which gets run, and this is responsible. This is where kernel hands over access to the system to user space. This is the first user space program, and by handing over access, I mean it allows the programs to ask for access. The kernel is the provider, but it provides a mechanism, it provides means to access, and it controls the access, manages the access, but each process can then ask the kernel through one of these interfaces. There are many interfaces like we discussed. One of them is the virtual system interface, like proc self status, let's say. So I'm currently, this actually shows me the status of the currently running process, which is cat. So this, when cat looked at it, it says, okay, this name cat, what's the user mask, this is a permission mask. Then it was, when it checked the status, it was at status running, so that's why it shows running. It has stopped after that. Then it has shows all the any additional information, how many signal interrupts and all of this. Yes, so there are other informations like proc uptime, for example, how much time it is the system has been up. Then obviously there are other kernel, let's say, for example, we have all this additional information which the kernel exposes. We looked at host name, for example, IO UDing disable. This is a feature in the kernel, IO UDing, which if it says IO, let's say UDing disable, it says 0, which means IO UDing is not disabled. 0 means false. it's not visible. So similarly, there are other settings which the kernel exposes, and obviously the one which we can directly relate to is the class, and this shows all the classes of hardware that is connected on to the system. For example, Bluetooth shows all the Bluetooth. Block shows all the block devices, which means which contains the all the hard disk, or the USB sticks that connected to. It's represented. It's the representation is shown here. Backlight, again the same thing. The point is everything there. This is the one of interface. Then there are other interfaces like syscalls and IOCTLs and socket-based communications, which allows the program to communicate with the kernel to access a particular hardware. But Linux doesn't have, or the kernel doesn't know how to access all the different hardwares, for which it requires individual driver modules. For example, it knows how to communicate it has a specific interface as to how a wireless module should behave, but every wireless module is created by different vendor, different hardware manufacturer. They can implement things independently, but what the driver module does is, so this is, let's say, kernel interface to, let's say, Wi-Fi. Then there is hardware manufacturer or manufacturer interface to Wi-Fi, let's say, which is the Wi-Fi. I'm talking about Wi-Fi, but you can place in any device. Basically, you can basically say Wi-Fi, memory, graphics card, no, audio system, anything, any hardware. So there is a interface. Kernel has a way of saying, okay, this is how a Wi-Fi device should function. These are the functions it should provide. These are the interfaces it should support. This is how we will send data through the interface. This is how we would connect, and all of that. And similar, but the other part is the hardware manufacturer designed the hardware, and it allows the hardware to be accessed in a certain way. Then the point is, kernel, the hardware manufacturer, there are many hardware manufacturers, so each manufacturer can have their own interface to their particular device. So that's why in this part we need driver module for Wi-Fi. This is where the driver module comes in. Think, okay, this allows the interface, the kernel interface, and also adapts that interface to the hardware manufacturer provided interface. So as far as kernel is, once the hard driver module is loaded and initialized by the kernel talks to the hard driver module. The driver module adapts or converts the signal or the operations accordingly to match the hardware manufacturer interface. And whenever hardware manufacturer, the Wi-Fi card responds back with the data, it also again converts it back to what the kernel would understand. This actually helps the kernel to use Wi-Fi. For example, let's say this is Wi-Fi, let's say Intel Wi-Fi. Intel creates hardware Wi-Fi, Intel Wi-Fi. This works, but then let's say I use Realtek Wi-Fi. Realtek is another manufacturer. Realtek, there is a hardware. I use the Realtek Wi-Fi hardware, and so the Intel Wi-Fi driver module would not work. I have to use the Realtek driver module. But notice the thing that the kernel doesn't have to change. The kernel still has one interface for Wi-Fi, to which all the different hardware manufacturers adapt to, and it provides a bridge or from the kernel interface to the hardware manufacturer interface. Now, since we know how these modules are loaded, and we saw a list of modules also, modules, for example, I can see the driver uh, RTW. My driver is something, this one, RTW898852BE. I will show you how you can get, we'll show basically experiment on this and how you can find out which driver is responsible for your Wi-Fi and all of this. But for now, this is my Wi-Fi module, and this is responsible for actually connecting to my Wi-Fi card or the network, Wi-Fi network. And the process which is responsible for loading these drivers, the thing is, kernel is the one which is loads the driver. Kernel loads the drivers, but user space program must request its loading. Request loading the driver. So kernel can load the driver. Kernel detects the hardware. It has the ability to load the driver, but the responsibility is delegated to user space program. So the user in some user space program must ask the kernel to load a particular driver. This is important to understand. The kernel doesn't load the driver by itself. One has to request the kernel to load the driver. There are many reasons for this. One thing is, one of the simpler reasons is you can, let's say you are testing out different drivers, you are developing driver, you have multiple drivers which support the same hardware, and if the kernel loads the driver, then there is no you have no control over it. But if kernel allows the user space program to request the loading of the driver, we can basically say, okay, we don't want we want a specific driver to be loaded for a particular device. For example, let's say IP link, which shows all the different network communication interfaces. This one is the Ethernet communication, because there is a Ethernet slot in my motherboard. It allows Ethernet communication. It is currently down because I have not connected any cable to it. LO is a loopback. This is a virtual interface which basically connects to itself. Then this one is the virtual. These two are actual hardware interface. This one is the Ethernet one, and this one is the wireless one. This one is status is up because it is now connected to my Wi-Fi router. And for example, if I just say mod probe -r, which stands for remove, and I say RTW898852BE, I say R stands for remove. This is a program which lets you ask the kernel to load or unload a module, a driver module. So this one is unload or remove basically. So if I say, we'll get to how you can find this module name for your hardware, but right now if I run this, okay, this is operation not permitted, I have to write sudo. This is it. Now if I say IP link, you can see the Wi-Fi interface is gone. Not because the Wi-Fi interface itself disappeared, it's still connected, but there is no driver module which can actually control this interface. So that's why although the hardware is present, Linux cannot use it, and that's why it's showing this is but if you see LSPCI, yes, there be a Wi-Fi network controller, this one, you see, 8852BE PCH wireless network controller. Linux still sees the hardware, but Since we unloaded or removed the module, the driver module, it now cannot access or use this network controller. Now if you say, let's say, and similarly, that's why IP link doesn't show doesn't show the usable link for wireless. Now again, mode probe, this is instead of remove, if he asks mode probe to load it, and we run this. Now if we see IP link, it is again, it came back actually. Of course the name is changed. It was earlier, it was WLAN 0. Okay, WLAN 0, but now it is WLAN 1 because Linux saw, okay, one device saw that one device went down and then came back up, so it gave it the next name. WLAN stayed same, then one came up. Now the process which is responsible for loading the device drivers, not loading the device drivers, kernel loads it, but requesting the kernel to load the device driver is this one, the udev d. D stands for daemon. As you can see, everyone has D at the end. Resolve D, udev D, key D, journal D, network D, system D, network D. But system D udev is the service which is responsible for detecting all. I mean, kernel detects it. It goes through the kernel detected hardware list, and there is a way which we will look at right after this. It asks the kernel for information regarding the hardware, and then it matches some information on the driver module side, and then it loads the driver module. But system D udev is already doing the work for us, and we want our system, we want to interject udevd. We want to do these things ourselves to understand how it is done internally. So that's why last time, if you remember, I used this use the QEMU emulator to actually set up a virtual machine where I loaded a custom Linux image with almost 0 application binaries. And if you have not seen that video, please go over and see the video. I think it's understanding Linux series number 3, I guess. I think it's number 3, from kernel to OS. This is what was the last video. We talk about how the PID 1 starts up. This process, we become the init process. We are, instead of system D, we provide a shell program as the init process to see how the system is at this point of time. Now we'll do the same thing, but because we want to show how to load the drivers and all of this, we will do the same, run the same RxRJ Linux, but instead of running it in a virtual machine, I will run it directly on this machine. And obviously I will not be able to, will be no graphical interface. It would be a TTY based interface, so which is why I will use a HDMI capture card to record the screen, and the quality might be a bit lower because it's not I will not be able to increase or decrease font size font size much. But let's dive into let's see this system. ls mod, remember this line, we have all the different modules which are already loaded in my system. If I say 115 modules, obviously we are not going to load all of these modules, but we'll still look at the process of loading modules, and we will load these modules for this very system, lspci. You see the same modules where we have a wireless controller or Realtek semiconductors, then Realtek Ethernet, also the same Realtek Ethernet, And there's the AMD GPU also, graphics card. I think where is the VGA? Okay, I cannot see it. Where's this one? This one is the VGA compatible controller, which is AMD Radeon's RX 6600. This is my graphics card. We'll see this system and we will load the drivers manually without using udevd, and we'll see what information that Linux provides and how we can ask the kernel to load specific and appropriate drivers. Okay, let's do this. So I'm now capturing using my HDMI capture card, my main system, and this is my boot menu. As you can see, there are four entries, but all relevant for different things. This one is obviously the boot setup, the BIOS or UEFI. Then this is the default one, which is where we were just in, the Arch Linux. This is my main system, the Linux that I'm running, and I have also set up Linux LTS version, which I generally don't use, but it is kept there as a fallback just in case there is some kernel regression and I need to use, and some device in my system doesn't get working, or if I need to basically fall back to the LTS long-term support version of the same Linux kernel. Both of them uses the same programs and same everything except the kernel. Yes, so and this one RxRJ Linux, this is my custom compiled Linux with almost zero by applications installed. All I have is the BGBox, which can provide me the different utilities like shell, mount programs, and all of this. The top and similar programs, the utility programs. It's a single binary which can provide all of the shell and everything. And then there is another is the module loader, because I'm loading. We are going to see how to load modules. So the default BGBox also provides a module loader, but actually it doesn't support compression all that well, so that's why I have the two binaries. Now if we are going to load into this custom Linux, the RxRJ Linux, let's see, and like you see, it doesn't have anything set up yet, so it just boots into the root shell. As you can see, who am I, if I see it doesn't even know that the name itself, root, the name itself, it doesn't yet is not yet assigned. And of course I have set up some things like the directory structure, which are essential for running the system, or like for example lib64, then lib. These two things actually points to, let me show you this one. Okay, it's a bit okay, the font size is a bit large for this one, but basically let me show lib, let's say. So lib is basically towards the right. You can see the arrow points to use /user/lib, which means it basically is a symlink to the user/lib itself. Similarly, lib64 is also there. And if we see user bin, you will see all of them are basically symlink to BGBox itself. All of them are basically symlink to BGBox, and there is no etc. As you can see, the configurations are not present, and instead of cmd I'm running this process init. This is the whole init process. This is around 18 lines of init process. The first I'll just go over the init process just so you know this is what we are doing currently. So this is BGBox. I'm installing BGBox so that I don't have to type in BGBox ls, BGBox mkdir. I can directly write mkdir because it sets up the symlinks, all the symlinks to BGBox. Then I'm obviously linking creating the symlinks to user lib for /lib and /lib64. bin and sbin also points to /user/bin. Then I'm creating these three directories, proc, sys, and mnt. Then I'm loading the virtual file systems provided by Linux kernel. The proc is for the processes, sysfs is for the system representation, dev tmpfs is for the devices, and dev pts is for tty. We're not going to use tty, I just edit it here. And then after all these things, we are just basically starting the shell, which is where we are currently at. Now if we see top, you can see the process PID1. The PID1 is actually this shell process, user bin ASH. ASH is a representation of shell, and it is a implementation of a corn shell by BGBox. And obviously we don't have much, but for example, we don't even have access to our NVMe drive itself yet. So for example, if we search for SDA, there is no hard disk installed on my system, and it cannot also detect NVMe because there is no NVMe driver loaded in the system. So now here we can actually try and load all the modules, but the thing is we don't have all the modules. For example, the modules are present in this directory, /user/lib/modules, and after this number is actually representing the kernel's release version. A good way to get this number is you name -r, which gives you the release name. Name -r, it gives you the release name. What's the release version name of the Linux kernel that is you are using currently. So mine is 7.2.0, and it says all these different files and folders in this one, and the modules are actually in kernel. Let's find on this one. Okay, let's not use find actually. The font size is a bit large. Kernel drivers. If I do ls, you can see there is only one driver package for NVMe. NVMe, there's obviously multiple things, but for now we will you load the NVMe driver and boot into a hard disk into a SSD partition which has more drivers, so that we can play around with all of this. So like we did for the Wi-Fi driver in my actual system, what we need is load the NVMe driver, and modprobe will basically resolve all the dependencies NVMe require, and basically order this line, and it will find in what's the driver in the directory where the driver is located, name NVMe, and then it will check in which other dependency modules are required for the NVMe. Then it will ask the kernel to load all of them one by one in the correct order, obviously. Now I do NVMe. Now nothing's changed, but we have now NVMe. Okay, we have all these different partitions, and obviously there are many partitions because my system has a real Linux and this custom Linux as well. And the thing is, the NVMe 0 and 1 is the disk, and P1, P2, P3, P4, these all correspond to individual partitions. And my P3 is the main Arch Linux partition. What we will use is dev NVMe 0 and 1 P5, which is the partition I have set up for my custom RxRJ Linux, and we'll mount it to /mnt. If you are seeing this, if you are not following along to what I'm saying, you maybe need to look at my previous videos where we did all of this in a virtual machine. But yes, I'm going to just go over each command once so that you get an overview. But if you want more details as to how this is working, you can see my previous video where we do this in more detail at a virtual machine. So now we will need to change the root, change into this MNT, and obviously MNT also has a unit process. And if we do this, now it basically asks for login, and of course I have set up the user root with a password and I have logged in. Now cd/ls, obviously it has something more information, more details, like for example etc, but it doesn't have much more details. For example, host name, password, and init.d. have set up some services, but I have not used any of them yet. And if you see lsmod, if I do lsmod, you can see the kernel has loaded only these 4 modules as of now, just because we loaded it, right? So NVMe, NVMe core, NVMe keyring, and NVMe auth. But now we need to load all the necessary modules that are required for this system. So let's see how modprobe NVMe works. What the command we ran was NVMe. This was the command we ran, and it obviously, because we have already loaded the module, it doesn't do anything more. It's the same thing. But what it does was, when to find a module name NVMe, what it does is it opens up not vpc user lib modules, and for the current kernel release, and let's go here first, user lib modules. That's okay. So we have all these things. Now if we open modules dot order, it contains all the different modules. Now if we search here NVMe, you can see these are the modules it has. I cannot visually select it because this is VI and not Vim, so I cannot basically highlight these things, but you can see this is, maybe I can keep it to top. Yes, so the first line, NVMe auth, NVMe keyring, NVMe core, and this is the NVMe. This is the actual module, nvme.ko. And this is how it finds the module. Then the second part is modules.dependency. This modules.dep. And now if we search for nvme.co.jst, I have a compressed modules. So that's why the nvme.co.jst, and it says, this, if you see, this is the column which to the left of the column, it shows what's the module name, and towards the right of the column we have all this the driver dependencies. Instead of using this one, let's do something like grep nvme.ko.jst and at modules.dep. Now you can see all this line. Maybe I can do color to help. No, I don't know why the graph is not coloring, but yes, this is it. As you can see, actually let's do this tr. For every space we want to replace it to new line so that it makes things a bit more visible. Yes, so the first line, this shows the actual driver name nvme.co.jst. This is the dependency that we wanted to load, and this has all these 3 dependencies: NVMe core, NVMe keyring, NVMe auth, and these 3 dependencies need to be loaded first, and then nvme.ko.jst can be loaded. Similarly, For example, if we say nvme, okay, we cannot, nvme core will also have its own grep. Let's say nvme core.ko.zst, and we say what's the dependencies for nvme core, and we search in modules.dep, and we replace the space with new lines. So nvme core also has two dependencies, the nvme kidding and nvme auth. Similarly, there is a whole dependency tree which needs to be accounted for while loading individual modules. Now we have in this system, I have all different modules. For example, ls kernel drivers. As you can see, I have all these things. For example, drm, where is no drivers, gpu, I guess gpus. So for GPU DRM, I have all these different drivers which are available for DRM. For example, AMD GPU, which is my graphics driver, is also AMD actually. Then AMD GPU, it has this AMD GPU.ko.zst, which is the module required for to load the AMD GPU. So let's see how we can manually manage the dependency tree first, and then after that, after we load one module independent, we will load AMD GPU, because we know in my system AMD GPU is the required one. We'll go over the individual process, and then we'll find out how we can detect which module is required. So for this, obviously we need grep AMD GPU.ko.zst, and we need what the dependency for this modules.dp, and we pass it to, so that every space is converted with a /n, which is new line, and it changes all these things. Okay, it has a lot of different mode dependencies, and we'll have to load the dependencies up, go over the individual dependencies, everything, and then we can basically load the AMD GPU module. Obviously this is going to be a bit difficult because this is too many dependencies to handle. Maybe we can find out a simpler dependencies to show you this, because doing this manually is a pain to resolve. There is another driver. Let's see the Wi-Fi driver actually. Grep rtw 889 8855 8852pe.ko.zst, and we search it in modules.dep, and we replace slash with. Yes, so this is the dependencies tree, and we'll load the modules from bottom up. So the first thing that we need to load is aead ko.jst. The way we load individual modules is ins mod. So this one is the insert mod. This is actually different from the mod probe that we use. So mod probe, if we do mod probe rtw 8852be, it will go over this dependency tree and resolve these things by itself. But we don't want to do this for now. What we want to do is we want to do these things manually. So ins mod, and then the path is /kernel crypto aead.ko.zst. It's loaded, and if we see ls mod now, okay, let me, this is too much. Let's say export ps1 equal to Yes, we don't want all of this information. ls mode, as we saw, we added the AED part also, and we need this one. AED is the first one, and actually it shows in the last in the dependencies, but because it's last, we need to load it from bottom up. Then we need to load nsmod kernel lib crypto lib arc4.co.gst. So now if we do ls mod, we are loading one module by one module at once. And if you see IP link here, now we don't have any interface, not even Ethernet, not WLAN 0 anything, but we will soon get here. This one, for example. Okay. Then comes the RF kill. We'll make these things a bit faster now. ins mod kernel net rf kill rfkill.ko.zst. Load this thing. Then come net wireless CFG80 for configuration driver for 80211. Then we need this MAC 80211. We'll do all of this. Then we come to our individual device driver. Wireless Realtek. Why did it? Net kernel drivers net. Okay, sorry. Kernel drivers net wireless Realtek RTW89 core.co.jst. After core, we need an pci.co.jst. Then 89 8852b 8852b common.ko.jst. Then after common, we need 8852b.ko.jst, and then the final part are 8852be.e.ko.jst. And now if we see ls mod, we have all these things loaded, and you can see which one is used by which. And now if we see IP link, we can see we have WLAN 0 as a usable hardware. Of course, it is currently at state down. If you see at the right, it says state as down because we are not connected to my Wi-Fi router yet. That's a different thing, but now the kernel can actually use this hardware. Of course, we could have just, instead of doing individual inserting modules individually, we could have done RTW89 8852BE, and this would have done the whole things for us. But obviously, we can do these things ourselves as well. But now, what we need is, because we loaded two modules, NVMe and RTW898852BE, along with all their dependencies. But the thing is, how do you know, or how does a program know which driver to load for a particular system? So for this, the kernel exposes many details. The first is the kernel is the one which is detecting the hardware. So obviously it shows this representation in, for example, class. We have all these different devices present here, but there is another way to see this, which is a bus. Which bus contains which devices? For example, there are PCI bus, for example, which is one of the core bus. Then there is a USB bus, the devices which are connected via USB. Then there are also platform bus, which there are many serial bus, I2C bus, HID bus. There are many buses. Buses are like, buses are like, at the core hardware level, buses are simply wires through which device can connect to, and at the system level, they allow different hardwares to communicate. It's the same bus, but every device can connect to the same bus, and the kernel can actually access each one of them independently, although they are connected to the same bus. Is a specific architecture involved which allows the kernel to control each one of them independently while using the same set of lines. A bus is actually at the core level set of lines, or set of wires, which allows signal to pass through from the kernel to the hardware. And the most common buses in a desktop system are PCI, platform, and USB. So if you see LS bus, PCI, we see all these things, and if you see devices, it shows you a list of devices. These are actually devices. Let's say if we see the 000000 and 0.0, sorry, 00.0, and we can see all the device information that the kernel has already detected. For example, if we see, wait a minute, 04, let's say, I noticed in my earlier system 04 was for the Ethernet controller. Let's see if this is true here also. Class might not be, but what you can do is we event, if you did the U event, it also contains all this information, but the important information is PCI ID, which is the 1022:18142. These are the vendor and device ID for individual for the device. For example, we can also load it by here, vendor, and I think this would be ID. No, what is the vendor, and there would be a vendor and device. Is it device? Yes, vendor and device, vendor ID and device ID. So vendors, every device would have their own unique vendor and device ID. Vendor is for the manufacturer. It's a unique for it's common for all the devices manufactured by a single manufacturer. For example, all the devices which are manufactured by AMD would have the same vendor ID for all of them. And then for individual devices, that it would have its own unique ID. Obviously, if you buy the same model, same hardware model twice, both of them would contain the same hardware and device ID, a vendor and device ID. But this is one of the key information through which Linux detects directly from the bus without any driver, because there is a PCI driver, how to access the PCI bus, that's baked into the kernel. So basically, that with that, the kernel can basically probe the basic information about the device. Now obviously the another information is mod alias, which also contains the same. If you see, it starts with PCI, stands for this device is connected via PCI, and then the first part is V. Going past the V, the first part is the vendor ID. It contains 000 padded at the front, but 1022, you can see 1022 is this one, the vendor ID, and then we can go a bit forward. Then you can see 1482 is the device ID, and there are many more other information as well. And this module alias, actually this is what kernel provides. We can use this to find out which module is actually required by the kernel, required for the hardware. And how it does is, if we see vi user usr lib modules, then for the current module identified by the release version, then modules dot alias, there is a file called modules dot alias. It has all this information. For example, PCI, it has the syntaxes. The first is the alias word, then there is the mod alias part. Also it contains wildcard. For example, it doesn't matter what is present between SV and SD here, and then star means anything goes in here, but the overall the pattern must match. And then the device driver name, which supports this particular device. So as you can see, this module actually supports all these defined module aliases. All that anything which resembles this, we can actually be supported by mhive underscore PCI underscore generic. Now we have something starting with PCI. It's a 0400 PCI, and it has 1022 at some place and 1482 then SV. So we can use this thing. So PCI dot start, it is VI regular expression for searching anything. 1022 D, then dot start anything, then 1482, then SV. If we search for this, we don't find it. Let's say 1022, this one, but it doesn't have 1482. 1022 dot star 1482, we don't have this. Let's say we do something else. 01 02 and mod alias. Here we have 1022 and 1483. Weird, okay. 1022 and dot star 148. Let's say 148. 1022 star. Why is 1022 not there? One zero two two and 1483. It has one PCI subsystem is 101453. Sorry, 1022. This one 149B 1022 1022 we just want to see one modules because there is easier way to do this. I mean, by searching through using a program, but we want to do this similar simply for one program so that we can test this. One 458 1584141A1. Okay, let's I think we'll have to do it another way and then find out the matching part actually. 1483. Did I see 1483? 1468. Okay, let's do this another way. So in mod alias, so instead we can see the device for devices star. For all the devices we can load the mod alias. Now let's say we want the first one, this one, and then this is the module. We can actually pass it to mod probe hyphen r hyphen capital R, which stands for resolve. So it basically it will go over all the module alias, the module.alias file, and it will try to match this alias is found in here. Okay, we need dollar here. Dollar. It says SSPS. Okay, we let's go over another module because I know this doesn't have. Okay, these modules doesn't exist actually. That's why we have been having no luck with this. Let's say 080 alias. Don't have this module. What can we do? Which one? Let's say 081 maybe. Okay, this is again SHCSP. I have tested this module doesn't come up. 18.0, let's say, alias. Okay, it doesn't have 18.1. Okay, let's know what, we'll do something like this one. For alias in this one, what we need to do is do echo alias equal to $al, and then mod probe hyphen r $al. So we'll see. Obviously, if we don't find, okay, let's try creating a script for this. Vm you can do it here itself. Let's create a script for pi modules.sh. So what we need is we need to find the modules get sys class, not class, bus PCI devices star mod alias, and let's say we call it aliases equal to $cat. We do this one and we say okay, echo, we go step by step. Now if we do modules.l, we need, why did we go alias is equal to $cat? Why didn't it do the new line? Okay, let me try alias is equal to $cat. Okay, or we can do something like this one. For alias in $cat sys bus devices, all the devices, and mod alias, we need to do echo $alias and done. Quoted. Okay, sys bus device, we don't have for ls sys bus bus PCI. Actually, I forgot the PCI word. We have all these different modules, and for each module what we need is for each module we want to know the module name also. Mod probe -r dollar alias, and for we also want a new line after each module so that we can basically track this. Yes, this is all right. Mod probe, obviously some modules would not have a module. Some mod alias will not resolve to a particular module. So most of the time, because this module is not present for this system, so those are okay. We need to ignore this. For this, we say any error we pass it to dev null. So std error, this number 2 stands for std error, std in, std out, std error 0 1 2. So number 2 stands for std error, and we are basically saying whatever is provided to the std error we just pass to dev null. Now if we run this thing, we'll okay, now see, we have all this information available, and we can basically try now. For example, SND SDA Intel, we can actually load this module, but what we will do is we'll try to find out how this match in module alias. For example, 1487, it has 1487 SV and 1458 SD. So vi user lib modules, we'll go over this just once to show how this is actually being matched. But yes, modules, we name -r modules.alias, and we need to find a 1487s 1458s SV and SD. 1487 1458 1487 s dot star 1458 s. It was not 1458. 1487 or 1458. Okay, 1487 SV. This is 1487 SV. You see, this one actually makes sense. 1487 SV. If there is 1487 SV followed by anything which is star SD, which means anything SD, followed by anything BC, and followed by anything SC, followed by anything I, and followed by anything, it resolves to SND SDA Intel, which actually makes sense because if we see, this has 1487 SB, then something something SD, something something BC, something something SC, then something something I, then something something. So this part is the one, the V starting from V0000 till 1487 SB is the one matched. This one from V000102D 00001487 SV, and we need SND SDA Intel. This is what we actually need. So now let's update our module. We don't need this thing, and we don't need this thing as well. Now sh modules.sh, it just shows us all the different modules which are required for different devices in the PCI, obviously ignoring all the modules which could not be resolved. But if we do this now, sort this and pass it to unique, we will see just a unique list of all the modules which are required to be loaded. Now we can say for module in $sh modules.sh sort unique, we need to do mod probe dollar module. We can basically load the module. We can basically say echo loading. We'll basically add this. Actually, that's what we can do this here actually in the this thing itself. Vim modules.sh. This is okay. We got all the modules. We need to add it in somewhere. Okay, we'll do it like this way only. MV, let's say modules to module list.sh and vi module load.sh. Here we will say module in $sh module list.sh and pass it to sort, and then unique. Do what we need to do is, let's say for now, let's say we just show loading module. We don't actually load the module, but let's see how this is in action. So it says it basically uses the module list.sh to list all the required modules, and then we can basically load the module. So instead of here, we can say mod probe dollar module. We don't need the brackets here because it's not present in a string. Now if we run this module load.sh, it will basically detect all the hardware using module list.sh. This is what it is using to read the modules. Then it will sort it and make it unique so that it doesn't load the same module twice. You get this, and then it will basically ask modprobe to load the individual modules. Module load.sh. AMD GPU, it's taking some time as you can see, and just give it a minute. Okay, it loaded almost everything except SHP, CHP, which is not found in the modules directory. Maybe I have done something wrong, but let's ignore that for now because everything else is being loaded. Now if we see, as you might already see, the resolution has changed a bit because it's now loading the proper it's now AMD GPU graphics driver is loaded now, and we can basically see this with class DRM. You can see card 1, all the different ports available on my graphics card is now are now available, and we can see basically HDMI A1 modes. We can see what are default modes that are possible on this GPU. 1920x1080. This is because of the HDMI, but if we see on the DP1, which is my main, okay, it's not yet connected. So based on the connected hardware on this particular slot, it will basically let's see. And similarly, class Zirmon, for everyone. Let's see the monitor name. These are hardware monitors, and you can see the AMD GPU temperatures are also available in HWMon 2 actually. HWMon 2, and let's see what it has. Yes, it has. I can basically see monitor informations like temp 1 input. It says 49 degrees Celsius. Similarly, there are temp, let's say 1, 1, 2, 3, and for every one we need label as well as input. Okay, why is it not working? Then okay, let's forget. I think this is something more to do with uh, the cell itself, which is not properly expanding this fields. But as you can see, we can basically now get the information about all the different hardware modules are loaded. And if we see now ls mod, there are many modules now. wc-l, we have 55 modules now loaded. This is how, for example, SND HDA Intel is also present. SND HDA Intel, this is the my onboard audio. Then there are more as well. For example, AMD GPU is also loaded, and the other required drivers are all loaded, all using these two script module .sh. The first one is for detecting the devices from sysbus PCI devices, and then the same thing for then the loading all the modules. Obviously, there are other buses as well, so let's load them. For, let's say, module list.sh. Vim is not found. Vim is not. Instead of PCI, we say USB. The same thing. Now, if we say USB, all the modules which are required for a USB. Now, if we say module load.sh, it will basically load all the modules required for this one. And loading BT USB, SND USB audio. This is my audio interface. Then the USB core. All of these are basically loaded. And now if we see ls mod wc-l, now it has 76 modules loaded. Of course, there are things like KVM which are not loaded yet, because this all we don't the KVM is a hardware feature, but we may choose to enable or disable this feature, and there is no hardware that needs KVM module to be loaded for us to use it. So for those modules, we have to manually load it using KVM. For example, KVM AMD, I guess this was the name. So now KVM is loaded. So similarly, there are modules which are not mandatory for the devices to function, but they still augment the capability of the hardware. Those modules has to be loaded by we can ask the kernel to load them manually. And for other things, for the mandatory device drivers, we can be what we did was module list.sh. For every modelias field present in /sys/bus/USB or PCI, then devices, and then the module we need to do resolve the alias to the module name, and we did that using user lib modules uname are modules.alias. We have all this alias present, and this is how it basically matches what module is required for what particular module mod alias, and using that we can basically the kernel brings us all these things. Actually, it's a part of the kernel project, the Linux project provides us the kernel. It provides as the kernel, then the modules, then the obviously the module info, like module aliases and all aliases. All these are part of the kernel project. So anything which is not present here, any open source driver that is present upstream, which upstream basically means it is accepted into the Linux kernel. So for those drivers, those aliases, everything would be um, packaged in the same from the kernel repo itself, taken from the kernel repository itself. So when your distro compiles, is compiled, it basically compiles the Linux kernel and the associated required modules, and packs in all the relevant modules to be used, and then it basically adds all the additional components like services, and like for example udevd. For example, if we see top here, you can see there is no udevd for sorry, n and r. So for example, we only have one process. All the processes in brackets are part of the kernel. These are kernel managed processes. So all the processes are basic. The only processes which are not are the ones which we started, and for example, and for them, and among them, the process ID 1, this is the shell process. This is what is the initial process that is running on the system. So now there is no udevd, so there is no way for the drivers to be loaded not automatically. There is no service to keep track of the detected devices and request the kernel to load modules automatically. So that's why we build a simple script, two scripts, module list and module load, which can together basically we can iterate over the list of devices in individual buses and then load the required modules. So this is how Linux system loads modules. And now if we see IP link, we can see the LO is present, WLAN 0 is present, then ETH 0, which is the Ethernet slot. Both of them are down because Ethernet is also Ethernet. There is no cable connected to the Ethernet slot, as well as there is no Wi-Fi. My Wi-Fi card is not connected to a particular router. This is it. This is how Linux loads the drivers. At this point, we have the system ready, the kernel ready, the drivers are loaded. The next step is obviously to load the user, set up the users, and allow loading of the user sessions and everything, and then go on to a graphical desktop if required. And after user session, we can start individual services. We can start a server or anything, and then if we require for a desktop system, we can also start a graphics, a display server, actually a graphics server, for example, like Wayland server or something, or AX11, and then we can basically use the system as a desktop. So in this video, we're going to stop till at here, and then in the next video we'll see how we can set up the user sessions and everything, so that we can, for example, we brought up the WLAN 0, but we didn't connect to a particular Wi-Fi hotspot or a router access point, and we'll get to that once we set up a user session, and we'll set up the necessary required services, essential mandatory services required for using the system and interacting with the hardware, because now the system is ready. We can use interface with the system, but for that we need to do programming, and I'm deliberately choosing not to use much of programming in this series. We'll come back to programming in later series, but for now we'll see how we can do the next steps. I mean, connecting to internet is the first, connecting to internet, and let's say starting a web server, let's say, or something, a program, basically any program which doesn't require graphical interface. These two are the prime objective of the next video, and then we'll think about how we can set up a GUI interface. So that's it. Now if we reiterate over what is needed for the for our system to load our drivers, let's do this in. Okay, so let's see how we can understand now, visually understand how we loaded the drivers. The first thing is obviously the kernel. This is where the kernel at, and we are running it. This is the user space program. This is our PID1 init process. This is the init process that was running, and the first thing we need is the interface. What we saw is the kernel detects the hardware. Let's do something like this one, and that's actually, let's do what we do is kernel detects the hardware. This is the hardware, and kernel detects the hardware. Then kernel and is present here. Kernel detects the hardware, and we can basically, init process can basically start another process as well. Another process as and when required. We can basically, for example, let's say this is top, or this is udev d, whatever is required, init process can basically start these processes. Actually, kernel will start it. It will basically ask the kernel. It will ask the kernel to start process, and the kernel would basically say, okay, let's give you top. Similarly, it will ask for kernel thing, and it will basically get you top. This is how the process generally works. And of course, now we have not done udevd because we don't want what we did was we got in a cell program, and then we use the interfaces, the sys interfaces, which is sys bus PCI devices. This is what we use to actually know about the actually devices. And for example, in my system, if we see cat sys bus PCI devices ls, and we have all these different devices present in this. These are the devices. These are obviously links to the this ls-1. These are all the devices present connected via the PCI slot. It basically, we can read the device and the individual mod alias. So for example, you can say ls devices star mod alias, and we can say get these things. So we get all the different mod aliases, and we can basically from get the after getting the mod aliases, we can ask the kernel to the diagram. I don't think this is get the model. Yes, basically, let's this part. What we need to do is iterate over sys bus PCI devices. We iterate over all of this. Then we match it to the mod alias from the modules dot alias file. This is what we did in say this one, pam user lib modules, rename our modules dot alias. Okay, this is what is being for example 1022 star 1487. This is was the, as we saw the last time, this was for SNDSD Intel, which was basically for my onboard audio. This is, and by matching this we can actually match this with grep 1022d dot star 1022d to 1487 SV. You can see this is the line that Modelias gave, and this is the line which is contained in the Modelias module.alias table, and it says it basically matches this pattern with the stars and everything, and it can be made usable by the module SNDSDA Intel. So that's why after this we basically say, okay, at this load the relevant module along with its dependencies. Actually, load the module. Let's say we can load the module, find the module in modules.dep file. Module and dependencies in modules.dep file. This is where we find the module. Then recursively load the modules. This is what we need to do, and obviously the whole process can be done by modprobe itself, which is basically a wrapper which basically checks all, goes over all this process, opens up the module alias as well, module dep file as well. So as you can see, snd sda intel.ko.jst. Okay, what was it? SNDSDA Intel. .jst. This is was the module name, and then it has all the different dependencies like this one. This one dependencies, SNDSDA codec, then SNDSDA core, SND Intel. This one, all of these modules are present, and all these dependencies need to be loaded accordingly. This is how modules are loaded, and obviously in and obviously in some system, in a normal system, most probably you are not using a custom script. You are using something like udevd, which is actually responsible for detecting it. Actually it also connects to the kernel via socket, so that when a new device is connected, plugged in, let's say through USB or something, and the kernel detects it in real time. It passes that information to the system udevd, and system udevd then basically loads the appropriate, asks the kernel to load the driver accordingly. So, and we saw all this, that this loading part is not part of the, if we see, we in the last video we saw about the process that the what is the kernel space and what is the user space. This is the kernel space, which where kernel is present, all the interfaces are there, process management, hardware management features, and this process, this is the user space. The user space is the one which is responsible for asking the kernel to start processes, start, as you can see, we talked about udev a bit, udev as well, which basically allows us, which is PID1 starts udev. Udev then basically use the defined interfaces to communicate with the kernel and load the different modules. This one, we did this without udev. We showed how to do this without udev just now, but in a normal system, in generally udev is the one which is managing the different hardwares. There is more responsibility to udev than just loading the drivers. It also updates specific permissions to the device driver files. For example, let's say we have ls mod AMD GPU. AMD GPU is loaded currently, which means there is a device DRI, which means direct rendering interface. There are two devices, the card 1, which is my actual card, and this is the render D128. Whenever a device or whenever a program needs to access my graphics card or anything, it needs to open up. This is for rendering only, this is for controlling, I mean for setting resolutions, setting refresh rate and all this. Anything which is more control level is this provides the full access, and any program which requires only to render, those can actually open this file. And for example, this file has this permission. You can see this file, this device, actually it's a device node. Device actually belongs to the video group. This one belongs to the render group. Similarly, for input, we have all the defined input, including mouse and joysticks and the different keyboards and everything. All these are being managed by udev, as in the permissions are managed by udev. And so by default, all these devices belongs to root user, but udev is the one which allows, using certain rules, it basically assigns specific permissions so that the hardware become usable for the different users. Of course, this can be configured, and so that which user needs to access which device. Based on that, you can basically configure udev rules to let, but the thing is, without the setting configuration of the permissions, by default only root user would be able to access the devices. So now this is it. Now what we can do is we can basically say, okay, the device is kind of ready, for the actual applications to run, because now we have kernel was already ready, and then we also loaded the drivers, which is part of udev. So we have loaded the drivers as well. And now what we need is we need to session manager. Obviously, networking services can work without a user session manager as well, but we'll talk about user session manager, networking services, and there is another, obviously, just for graphical user interface. We also need to handle this. So this one, and this one. These two might come in a single video, but the thing is, these are the 3 steps that we need to configure now for a for a usable system. Obviously, there are much more components to it, but the essential, I mean, these two are obviously the essentials. Then graphical user interface will just add it because it's kind of fun to have a graphical interface, and having we will try to set up something like this system where you can use Firefox, or we can use OBS and all of this. For now, we have loaded the drivers. We are one step closer to achieving our complete system, which we are configuring by ourselves. And in the meantime, in the process, we are understanding how Linux works in general. That's it. Great.